بسم الله الرحمن الرحيم والصلاة والسلام على رسول الكريم. Monsieur Dahmani et Monsieur Djabour, en vue de l'obtention du diplôme master, vous avez demain jusqu'à 25 minutes pour exposer votre thème intitulé Realization and Automation of PV Power Rocket Machine System. تفضل.
Firstly, I would like to thank those of you who are present here today. And I would like to read with these two meaningful quotes. The first one by Thomas Edison. He said, "I put my money on the sun and solar energy. What a source of power. I hope we don't have to wait until oil and coal run out before we tackle that." And Bill Gates said, "Robotics and other combinations will make the world pretty fantastic compared to today." I would like to shed the light on the two words, solar energy and robotics, and present to you our title titled Realization and Automation of a PV-powered rocket launching system. Presented by myself, Jabor Yusuf, and my colleague Thème Zakaria, and supervised by Dr. Zakaria Abdallah. The presentation today contains firstly of an introduction, and then followed by the definition of energetic autonomy, and after that the power system and the orientation system, and finally targeting and missile launching and accuracy. Starting with the introduction, we can say that robots has gradually invaded the human lives, consistently becoming an asset in most fields, and continuously pushing humans into their development and their manufacturing. Due to human limitation in terms of energy and ability, the researchers and engineers in this field have been leading the studies that benefit technologies in a way that would enhance and develop or overcome challenges that is in the way of making the human life easier. Integration of the renewable energy sources is the main concern that's being handled right now, nowadays, to enhance the robotic of the energy autonomy. So what is energy autonomy and what is the proposed solutions in our study? As a definition for the energetic autonomy, it refers to the ability of the system to maintain itself in a viable state, meaning that it works successfully and without any failure for a long period of time. Its behavior must be stable, and in order to not yield in an irrecoverable debt in any vital resources. Our system contains two main subsystems. The first is the PV powering system, and the second is the missile orientation subsystem. The PV powering system role is to assure the the power electric transfer from the PV panels to the second subsystem, which is the second subsystem is constructed in a way that allows it to position itself in two desired angles in order to reach the target, in order for the missile to reach the target. First, we start with the power system. The power system contains a PV panel which is directly connected to a DC-DC buck converter controlled via an MPPT controller. The DC-DC buck converter then feeds the battery, which will eventually feed the system actuators of the second subsystem.
And now we start with the PV panel. So we have on this line here, we start by proceeding to the PV cell model. So out of many PV representing models, the single line model has been adopted due to its simplicity, and we can say that the following equations demonstrate the PV cell mathematical model. We have the photocurrent, the saturation current, reverse saturation current, and current through the shunt resistor, and the output current. And after building the PV cell mathematical model, we have chosen a certain PV panel, which has the following characteristics. It has a rated power which is equals to peak power which is equals to 14 watts and 21.24 volts for the open circuit voltage, and the short circuit current which is equals to 2.55 amps. And we have it has the number of cells connected in series, 36 cells, and the number of cells connected in parallel, 1 cell. the ideality factor of the diode equals to 1.6, and we have 0.1 ohms for the series resistor and 215.405 ohms for the shunt resistor. At the same slide, we have the next characteristic, which represents the IV curve for generally for any given PV cell. I would like to highlight the main parameters extracted from this figure. We have at 0 volts, we can highlight the short circuit current, and for 0 amps for the PV cell current, we can extract the open circuit voltage. Every cell has a maximum power point, which is the coincidence of the optimal voltage and the optimal current. Now, after we built the mathematical model, we proceeded next to the simulation result under software simulation MATLAB. So, the simulation has been achieved according to 2 cases. First, we maintain the temperature, and then we maintain the radiation. By maintaining the temperature, we have these results. This figure represents the PV power variation extracted with respect to different irradiations. And the constant temperature, which is equals to 25 Celsius degrees. It illustrates how sensitive the power is according to different irradiations. A relative the direct proportionality resumes the relation between those 2 parameters. Starting from an irradiation from 0 watt per meter square up to 1,215 watt per meter square, an amount of power is produced from 8 watts to 15 watts respectively. For each curve, we can remark that the power is increasing from 0 to reach its maximum power point, then decreasing again to be equal to 0 at the open circuit voltage. And likely, we can remark that the open circuit voltage is slightly variant with considerable irradiation variation. On the following curve, we have the IV curve. So we can see that the short circuit maximum values increases each time the irradiation increases. Then the PV cell current remains constant, except a very slight ignorable decreases. Being over the optimal voltage, we see that this current decreases or takes a very fast decreasing behavior to reach 0 amps with open circuit voltage. Mostly, we can say on the next figure that with maintaining the radiation constant, which is equals to 1,000 watt per meter square, we can put the mark that the open circuit voltage here has a large band variation, unlikely the case where we maintain the temperature. And for the IV curve, we remark that the open circuit voltage has also great variation with respect to temperature. And now, after obtaining the PV panel characteristics, we pass to the MPPT algorithm and buck converter. So, in this study, a buck converter has been chosen due to its simplicity. Simply, a DC converter is a topology, which consists of a controlled electronic switch, which is in our case a MOSFET, and the non-controlled electronic switch, which is a diode. An inductor is used to store and release the energy to the load. The capacitor is used to filter and smooth the output voltage. On the same slide, we have the chosen buck converter parameters, the inductor value, capacitor load, which is purely resistive to the frequency and the current and voltage ripples. And now we proceed to the perturb and observe MPPT algorithm. this script MATLAB code, which controls the buck converter, we have the defined function which has as inputs the voltage. Next we have the simulated block. From left to right we have the solar panel which is directly connected to the PV buck converter. This buck converter is controlled by the perturb observe MPPT algorithm which generates the desired duty cycle. This buck converter feeds directly a purely resistive load. The irradiation input, which affects our PV panel, has the following form. It is a scalar form. And now we proceed to the important point of this PV system. The simulation results as next. The blue curve represents the ideal theoretical power extracted from the PV cell without MPPT algorithm. And the green curve represents the power curve extracted.
The PV power system feeds directly the orientation system. There are many ways to model a robot. But amongst the literature, there is one highlighted way. It's called the Denver-Hartenberg. The Denver-Hartenberg is relatively uncomplicated when it comes to the process of obtaining the direct and inverse kinematics, which brings us to this one. The direct kinematics were also. Kinematic equations of the robot to determine or compute the position of the end effector from specified values of the joint parameters. The use of the Denver-Hartenberg convention yields the link transformation matrix shown, which is also shown in the thesis. In the robot characteristic, the simulated robotic arm is characterized by the following parameters. Mechanical articulated structure. Its mechanical articulated structure is a serial manipulator. It has two degrees of freedom. Its type of joints is revolute, and it has a rotation range of the first joint, 360 and 19 degrees for the second joint. With the previous characteristic table in mind, we obtain the following DH parameter. Once the parameters are applied, a basic model of the robotic arm and frame joint are structured accordingly. The following figures represent the robot links and joints. The first matrix shown in the table demonstrates the transformation matrix of the first frame with respect to the base frame. The second transformation matrix represents the transformation matrix of the second frame with respect to the first frame. And finally, the third transformation matrix is the transformation matrix of the second frame with respect to the base frame. Therefore, the joint values and position, the figures represent from left to right the end effector position with respect to the base frame and the joint values evolution in time. As you can see, it's all the values are gradually and in sync evolutionary in time, and the negative values represent the clockwise direction of the movement. Here is a demonstration of an animation of the workspace that can be used with the robot. The robot will attempt to turn 10 turns while targeting up to 19 degrees.
And now we proceed to the targeting and missile motion. To plot the motion of the missile, we've used a MATLAB code script, which is described on the following figure. So all those equations are abstract physical equations which are put here on this MATLAB code, and this code generates these results here. So we have a Cartesian coordinate frame. We have a desired target, which should be reached by the projectile. So we conclude that the implemented MATLAB code works as well as good because it reaches its position. And now with the conclusion, we can say that the implementation of the MPPT algorithm on the PV system has provided a close result to the ideal variable power, expanding the efficiency of the power outage, hence providing more power to either use directly or stored, which will enhance the energy autonomy of the system. Based on the simulation of the robotic arm, the Dina-Hartenberg parameters with chosen angle values have proven that both of the first and second joints are correctly structured as desired and to obtain the wanted orientation of the held missile. Concerning the missile motion, the simulation results has proven that it's sufficient to know the target coordinates to obtain the first joint volume. Knowing the initial velocity of the missile is needed to determine the right joint volume of the second joint. With the two joint values, the position of the missile holder can be assured using the transformation matrix. As a conclusion, and based on what's previously stated, the aim of this study has been fulfilled with respect to the firstly outlined goals. Thank you for your attention.
Bon, je tiens à vous remercier pour l'exposé. Sans tarder, je passe la parole directement à notre examinateur, monsieur.
Thank you, Mr. Chairman. Thank you very much for your presentation. Actually, I liked the English. It was very nice. It was very encouraging for the other students that are here, but unfortunately no one is here to see that. Well, the subject is a very important subject. It's a very, very nice subject. And I see that the subject is composed of two parts.
Yes.
And each part actually, honestly, is a very heavy part. Both of them are heavy parts. So I was wondering when I saw the title, how could they manage to make all this in this thesis? Well, it was the nice part of my intervention. Now let's see the other side. Firstly, I was looking to the first chapter. It was, no, I think first or second. It was talking about robots and so on.
Yes.
I don't feel that this part is very linked to what you have done. I mean, robotics is very, very, very huge field. So, but I was looking here and reading some of this movement and others, and I was trying to find the link with your system. Is it very linked to your system?
So the very first chapter is generalities about robotics.
Yeah, I know. I can understand you. But even when you make generalities on something, try to be focusing on a part of it. Because if you talk about robotics, it's infinite world.
Yes, due to the huge universe of robotics, we have focused our attention on the kinematic part of the robotics. So we studied the kinematic.
Excuse me for this. Kinematic is for all robots. So you are not focusing on something. But even kinematics, what do you mean by kinematics? All of them are kinematics.
Yes, are you asking us what type of robot?
I'm asking, I feel that it's necessary to talk about all this.
Okay, let me clear a point here. You want to observe the link between robotics and our subject.
No.
So, I'm sorry, I'm not following.
No. You're talking about a very, very, very large field.
Yes.
I mean, if you have focused on part of robotics, I mean, you talk about robotics and then you focus on special parts. What kind of robotics you're going to study?
Yeah. We mentioned that on the presentation. If we didn't do these generalities, we couldn't classify our robot. Which range it is classified?
And
I
our
think we
robot
can
is
respond.
classified under the signal manipulated robot.
So without these details, we can't classify our robot.
Okay.
The mechanical structure. Like if I give you directly the chosen robot here in our study, you won't get the point where it is, what range it is put this robot here.
Yeah.
So it is a serial mechanical structure with 2 degrees of freedom.
Unfortunately, due to the actual situation, you didn't make realization, right? You didn't realize the system.
Yes.
But for this point,
Actually, we've done our possible to make the realization finished, but due to this pandemic situation here, we've bought some components, but time was very limited and still needed some components like oscilloscope.
I can understand this. This happened to all the students.
Yeah, unfortunately.
But yeah, in this context, because I will start from the last line. As a conclusion, and based on what previous stated, the aim of this study has been fulfilled. Do you think the aim of this study has been fulfilled?
But you have to continue the sentence.
With
respect to the firstly outlined goals, and you have to look first to
what are the first of the
So we had to ensure an intelligent extraction from the PV panels to the actuators of the robot, then orientation them to the desired position in order to reach.
Wait. For this, I didn't see all of those or said now. I didn't see it. Where is it? I mean, where is what you are seeing now in your thesis? Show me page. I would like to see it.
So the first
Page
59.
Huh?
Page 59.
59.
This is the first point.
58 and 50.
Yes.
Okay. You have the comparison figure.
Yeah, but what is this?
It's the comparison between the theoretical power and the algorithm power.
Are you powering the system with PV directly?
No, we have the store.
No, yes.
No.
Wait, let's start with you.
Yes,
Why yes?
we are powering the system through a power converter less controlled with an MPPT algorithm.
Okay, then the energy.
Why no? He said yes because. Why you said
We are not the same way, but I have to explain to get my point.
So did you calculate your motor power because it is motors?
Firstly, we calculated the power with
There's 2 stepper motors.
yes.
And the rated power needed was around
About
40 watts.
What?
40 watts.
40 watts?
Yes,
That's all?
for each one.
Are you sure about this?
Yes.
So it's very small missile.
Yeah, it's prototype. It's prototype, not the real one.
The missile that we based our study on was it's called the spike technique.
Actually, it's missile, not missile. They say missile and missile.
Okay, doesn't matter. But
Missile. The missile that we based our model in was called spike, I think, and it's
Spike.
around a kilo or so. It's a guided missiles that targets tanks.
yeah, it has a small size, around I think 50 centimeters.
So it's not really.
Yeah, but it is used in the Iraq war, for example. It is constructed in Israeli inventors. They made this rocket.
Look, generally in these kinds, they use hybrids. They don't use parts alone.
They
Hybrid system. You know what's hybrid?
Yeah.
I mean, they use
Multiple
human power with solar power with other kinds of
Yes.
Yeah.
things.
The missile does use hybrid energy, but the larger, however,
Yeah.
the larger
Okay.
could be powered using electricity.
Yeah.
Yeah, of course, but I mean the source, not the power used, the source.
The source of the launching system.
Yeah.
Yeah. Yeah.
What is the launching system?
The launching system is a system, as we say, it is a robotic arm.
Look, The launching system doesn't control the orientation.
Yes.
So it carries motors.
Yes.
And motors need energy. And the energy is calculated based on what?
Based on the choosing stepper motors.
No. I mean, even the stepper motors are chosen based on what?
Based on the torque.
The torque.
They can handle, yes.
Yeah. Do you know the real torque of missiles or the system?
The real torque.
Yeah, of course. Do you have data or just you were imagining the system?
We had data at first, but when we canceled the realization, we didn't see the need to put it in the thesis.
I think it's very important to put it because you're making design, and design you need data, or at least put your data. But without data, how are you going to make your?
That's true.
We did use the data, but we didn't put it in the thesis.
And that's due to we canceled the realization part, so we didn't see the need to put that. That's why.
Okay. Now back to your system. So it's solar panel feeding the back converter, and the back converter is feeding the motors.
No. Feeding the battery, you have the storage part here.
Well. I'm putting the schematic of it. Because you're talking about PV panel feeding the motors. This is what you have said.
You followed my presentation.
Yeah, because I was saying in my question, what is the need of batteries here? So you're not feeding the motor, you're feeding the battery.
Not directly, yeah. The battery is
battery directly.
storing energy, yeah.
Directly the battery.
Then we have to feed our actuators, robot actuators, from the battery.
From the battery.
Yes.
Not from the PV.
Yes. And we mentioned that. It is actually in the presentation.
I asked the question and you say no, yes, and I was waiting this answer.
So it's just a misunderstanding.
Yeah. We are all the same point.
Okay. Page 59. Well, I didn't speak about the form and the others. Well, I feel because I didn't read it from paper, I read it from my screen. I feel it was a good book. I feel because I turned some pages with inside. Well,
That's another.
except some figures now, some equations. It was like copy and paste. Yeah, it was copy and paste.
I have written every single equation.
Yeah, I don't know. Maybe on my screen it was very faded, not clean one.
Okay, maybe the font and the size of letters.
I can assure you that I have spent hours.
Okay, I believe. Yeah, 59?
Yes.
Now this figure, 51.
51?
Can you explain it again?
51?
Yeah, because I see a lot of swinging before.
Sir, 51 or 59?
51. No, page 59, figure 51.
Okay. So, what's the question?
Yeah, can you explain it again?
Okay. The blue curve represents the ideal
Okay.
PV power.
Yes.
And how we can judge the MPT efficiency, perturb and observe?
Okay.
By comparison to the ideal theoretical power.
Okay.
Putting them together, we have these results.
Yeah, but why we have this swinging in the first part, and when we put another steps, we don't have any swinging?
So the reason of the oscillation.
Yes, please.
The reason of the oscillation.
Go ahead.
The reason of the oscillation is because of the initial value of the set.
No.
Yeah, continue.
And also the step iteration. It was a bit small.
Step iteration.
Of the set.
The
Okay.
It was a bit small. The reason there are no oscillations in the second and third bumps because the difference between the irradiation value was not that big.
Look, if you are talking about step iteration, you should put this aside.
Not step iteration, not step iteration. The step in algorithm.
Yes.
The step in algorithm.
We have.
It's not step of iteration, step of either of duty cycle. You perceive the beyond duty cycle.
That is what I said.
And is the target, and when he reached the ppm,
Okay.
it's there is no oscillation.
Yeah, it affects the behavior if it will be slow or fast. This step in into the cycle.
Yeah, in this case you need to put this alone and the other one alone. I mean, you should overpass this part to tell us that it can respond in this way with different steps. But like this, I see that this response is not the other. So this is why I was wondering why it is not the same. This is the first, for me, as automation. For automation, I can say this is the first order system and this one is something like third order system. It is the third order system.
Can you let me respond in this point? Can you let me respond in this point? In direction, and he made a step in another direction. You know?
Sir, should I clear you something here? These oscillations are due to this one. This one here.
Yes.
Then you have to refer to the cycle of this one, each iteration.
The angle of iteration, not the iteration of simulation.
This is why I said you needed to overpass this part because it's not transient due to the system, but due to the algorithm. You should put it aside, then take different steps because the other steps are very small. And then take different steps which are really clear.
Yes.
Then I can see that, oh yeah, it is the first order system. But in this case, I believe you.
Yeah.
But I needed an explanation for this. Because I'm in the first part, I see third order system, then it becomes first order system. Something happened inside. Okay?
We should to note that in the final version of the decision.
Okay.
We should to add it.
Yeah. Okay. How many motors you have in your intervention?
What?
How many motors?
Motors?
Two-step motors.
Because we have the robot has two degrees of freedoms.
Did you talk about the control of these motors? The controlling system of these motors?
Actually, if we proceeded to the realization.
Yeah, I know, I understand you.
Yeah.
But at least you have a vision of your system.
Yeah, we have.
I mean, you should write it your vision because the point that you're not talking about, in this case,
Okay.
you should stop in the not first part. PV powered rocket, and you don't talk about automation.
I got you.
When you talk about automation, you should tell us about the chain
Yeah.
that you are proceeding to activate your motors.
Okay.
And how do you calculate the signal? I mean, the signal that gives you the precise, the accurate
The angle.
angle.
The PWM signal generated from.
And where do you copy? Where do you get your coordination?
Coordination.
From
The user.
targeting algorithm that's being simulated.
The user has to tell us what's the coordinates on the Cartesian frame.
This is the true answer. The other one was out of the way.
I was about to get to that.
Okay.
If you go to the Alex, in
This
the-
simulation, did you maybe make it yourself or you found it in MATLAB?
We made it by ourselves.
actually was going to do a simulation in MATLAB, but the toolbox didn't work on the correct.
And this is MATLAB or
No, this is a software called Robo Analyzer. It's
Robo
an academic-
Ah, okay, so you didn't make the graphics. Everything was there.
Yeah.
Everything was done. Now, about the coordination.
Yes.
What kind of coordination you use?
Cartesian coordinate system.
What is it?
Cartesian.
Cartesian.
Yeah.
Okay. Cartesian system.
Yes.
You mean
X and
X,
Y,
Y, Z?
Yes.
Is it enough?
I think it is.
Are you sure it's not? You know that X, Y, and Z, we use it for translation.
Yes.
And we don't have translation.
But it is sufficient to represent a 3D object on the space. And our target is generally on the ground.
We are not talking about the target. We're talking about your motors.
Okay.
They are controlling the angles.
Yes, yes, exactly.
How many angles are you controlling? 2 or 3 or 1?
Two joints, revolute joints, not
Transition. If you may let me speak. The modeling of the robot was used, was modeled with the Département method, which works with the linked transformation matrices.
Okay?
The linked transformation matrices have data about the transition and the rotation of an object in each joint.
You're talking about the object. I'm talking about the legend.
yeah.
I'm saying in each joint has a Cartesian frame. You get what I'm saying?
No.
So, if you look closely at the if you look closely at the models in page 62,
You can see that every joint is assigned with a Cartesian coordinate system, X, Y, and Z. And then we have to do the direct kinematics of the robot. We have to get first the transformation. What?
I'm controlling motors.
Yes.
Motors are doing rotation. I need angles.
yes,
You're controlling a step motor. Give me the angle. You don't give me the angle. You give me the object coordination. So I'm asking about the angle. Theta and phi.
Yeah. Theta 1 and theta 2.
Theta 1, theta 2.
yes.
Yeah.
Okay. You're not. Did you give me the theta here? In this?
We've done initially
In the simulation,
The equation motion.
simulation. Yeah. Equation motion.
the client or the user will put the coordinates of the target.
And then
And the coordinate is based on the base frame of the robot. You get what I'm saying? So in the base of the robot.
For me, I need theta 1 and theta 2.
yes.
That's all.
If you need
Did
this.
you mean
calculated?
Did you mean it? Here.
Yeah, we made it.
Give me the equation.
Okay. So if
Maybe
you go to the annex, page 69.
So,
If you go to page 69, there is the algorithm that calculates the angle.
69.
Yes.
69. No.
Okay.
No, I don't agree with you. I don't agree with you. Don't give me my algorithm. Algorithm is based on equations. What I think?
Yes.
Where is the equation of
That
theta?
are in the second chapter.
Okay.
I just wanted
You needed to go after it. I don't need the algorithm.
The algorithm is just an implementation of the old
Equations.
Where page I
Okay.
should see that?
All right. Page 14.
starting from page 45.
56.
45.
Yeah.
Okay.
Take the decision. 45, 46. 46. 5. 5, there is no difference.
Okay.
46? Oh, no, 56.
Okay.
40. Okay.
This is a whole mathematical proceeding.
Yeah.
Given the coordinates of the target, we get the joint's value theta 1 and theta 2, which will be then given to the robot, which will use the Dinavet-Hartenberg convention to position itself to the desired position.
The equation you are looking for is equation 54
Yeah.
at page 49. Excuse me for the
49.
mistake. Yes.
Yeah. Page 49, equation 54.
Where is theta 2?
Yes, theta 1 is.
I can see theta 1. Where is theta 2?
Theta 2.
Okay, theta 2 is in page 50, the equations 56 and 57.
Yeah, I forgot to put 2, just under the theta. It's a mistake.
The 57 there's nothing. 57, are you sure?
I said the page 50 and the equations 56 and 57.
Ah,
Yes.
50 equation.
56 and 57.
Yeah,
The equations.
theta 2, but here just there's a mistake and you can see 2.
Okay, this is theta. Is it theta
Yes.
2? So, correct.
Yeah.
Yes, I will.
Yeah, we will. This is just a mistake of text.
Yeah, because I was looking for it.
Yeah,
I didn't find it. So, okay.
We will correct it.
Okay. I have a lot of questions, but my colleagues now are urging me to say thank you very much for your presentation. It would be very nice if you have made it, but unfortunately I can understand the situation. Thank you again. Thank you, Mr. Chairman. And
Moi, je tiens à vous remercier, monsieur le maire. Donc, je passe la parole au deuxième interventeur, monsieur Thème.
بسم الله الرحمن الرحيم والصلاة والسلام على رسول الله. Donc, thank you, Mr. Chairman. I thank you also our student Ahmani and Jabal for the quality of your presentation. Okay. Let me say that I am very happy to see our student use English language in their research activities. Okay. I have a strong question and some remarks. I cut with the remarks. It's a very happy subject with short introduction.
Okay.
Okay? You don't present the problem and the details of your chapter. Okay? The first question, in the page 3. Page 3. Page 3. Could you explain me these new words?
What are these words?
Page 3.
Yeah, where exactly?
Okay? In the first paragraph,
Okay.
present the recent development.
Okay.
Please.
Allow me to start it. Recent development in robotic course has made
Recent development. 2. I have new words for me.
Yeah.
Paragraph 1. Affordable.
Word? Affordable. That means share.
affordable.
It's not expensive.
Yeah.
Affordable is the opposite.
Yes.
Okay, yeah.
Moon.
Affordable c'est
Moins coûteuse. Moins coûteuse.
Préoptimal du monde.
affordable ça
Plus moderne.
plus moderne.
And I have new words, hazardous environment.
Hazardous, that means
Random.
Yeah, okay. Okay. My second question. In the same page, you spoke about motivation. You said that you participate in the CIAA preparatory competition.
Yes.
Could you tell me about this competition? And my second question, is it the same rocket?
It is, no.
No, okay.
Okay.
So the competition was
Between universities.
between
It's inter-university competition here, but those three top classified will go to the United States in order to compete to represent Algeria in let's say this international competition at the USA, New Mexico. But we get the 6th place by the way among 12 universities.
Okay. I think that you participate in Liga.
Yes.
Could you tell me about this competition?
Okay.
really
It was, we were asked to make a rocket and the satellite prototype. And we, the electrotechnical students, we were charged to make the satellite PV feeding. But unfortunately, there were no supply, so, but we couldn't do it.
couldn't the small cells to fit into something.
Okay. In the page 22, in the conclusion, in the first paragraph, page 22.
Okay.
The first paragraph. In the conclusion, in the chapter, we have presented the definition of some technical terms and the review of literature related to the field of model, identification, and control of robots. Is it true?
We will frequently come across these terms in this thesis, and some of them will be reformulated in a more analytic or mathematical way.
Is it true? You speak about model identification and control of robots.
That's not actually.
I didn't see this model and identification of robots.
We explained the models of the types of robots, the mechanical models, the mechanical modeling. I mean these.
Classification of robots.
Not identification and
So
control.
this is
Not changing.
yeah, we have to correct it.
In page 4, robots. Page 4. Robot. Your robot is
You're not.
in page 4. Robot is
Just give me a second.
Okay. You must have the conclusion of the chapter 1.
Okay, propose your point. Conclusion. Okay.
Okay. Page 4.
Page 4. Okay.
Okay. Robot.
Yes.
Part 3, part 2, robot.
Yeah.
You say that robot is a mechanical device. I think it's a mechanical device.
Yes.
Generally.
Yes.
Yeah, that's the general case, but you can find.
Robot it's a mechanical device, not.
Yeah, but you can find in manufacture a pure mechanical robot. There is no electrical components.
Could you give me some example?
For example,
For example, cooking.
Yeah.
It is a robot. That's
It's a robot, but
Yes.
it's electromechanical. It's not a mechanical robot. I think that.
but this definition, I think, is too
I think
full.
essentially
Yeah.
the robotic field is a part of the mechatronics field. Yes?
Yeah. it's not-
Okay. And in the same paragraph, robot is a mechanical device containing electrical, X-ray, and IT
Yeah.
parts.
Yeah.
What IT?
Information and technology parts, which has sensing
You should have it.
data. Huh?
You should have it.
The word device is not very correct, actually. The word device.
What's the accurate one?
Device is system, that's a system.
System.
But device is like
Compound.
parts of
Compound.
components of.
Yes.
Yeah,
It's not really a device. When we talk about device, we talk about many devices in that part, but we don't have many devices. It's like
Actually, point.
The next page, page 5. Not yes, page 5. And page 4. You monitor drive. We speak about page 4 and page 5.
Page 4 and
The
5.
part 3, 1. The word joint. Why is not this first paragraph by these limits?
Yeah, this
You
returns.
can't start a new paragraph with this.
Okay.
It's the same error in the next page. This might be joint. I think I can't pronounce it correctly.
Yeah, it's a joint. Yeah, revolution joint.
Okay. Okay. Page 28.
28.
28. Equivalent model of TV.
Yeah, single line.
Okay. Can you explain this figure?
Okay.
The dot and why use this model?
Yeah, due to its simplicity, it is simple to work with. And its equations are not that complex. So we wanted to proceed with this model in order to make it just easy. Why taking one model which is complicated just to obtain the PV cell characteristics? So we could do it just with this model.
In the page 37.
What's it?
37.
27.
Sorry, 27 or 57?
It said 30.
37.
Yeah. 37. 37.
Yeah.
To supply in there, you must use everything ugly.
Yes.
Okay? Except the power, not the power.
Yeah.
Okay?
Yeah.
Here, you give flip shots. Okay?
No, so which page?
Page 30, from 37 to 39.
From 37 to 39.
Okay?
37. Okay, the flow chart, yeah. That would be the inverter and observer argument.
Can you explain me this flip shot?
Yeah.
Okay?
We have as inputs the PV panel voltage and the PV panel current. Then we have to calculate, we have to
compare the power in the current time and the following time. If the power increases, we will check for the voltage. If the voltage increases, then we will add the equation to the duty cycle. If the voltage decreases, then we will add a negative value to the duty cycle. And if the power decreases, we will also check for the voltage. If it increases, we reverse it.
How do you do that?
by microcontroller.
Yeah, of course, by a controller, but how do you do that?
How do you do what?
With sensors.
Play it on the
Current
duty
sensors
cycle.
and the voltage sensors.
No, how do you play on the duty cycle?
The duty cycle using the PWM. So,
Practically. Do you know that you need a regulator inside?
Regulator to regulate what?
How the duty cycle? The duty cycle you cannot control it like this. You need a regulator inside. The PI
Feedback.
Yeah, feedback with PI at least.
Regulator.
Huh?
So we use that and microprocessor and
It is inside the microprocessor.
Okay, so you have to.
Okay, I need to discuss with the other supervisor. But what I said was true. I work on this.
We think that the climatic conditions can affect the pure output.
climatic conditions, yes.
Yeah.
So the PO algorithm extract the maximum power in certain climatic conditions.
Whatever the radiation, either the temperature, this algorithm here assures the extraction from the panel the optimal voltage by imposing the right or the perfect impedance into its limits.
Okay. In page 35, the presentation of an object in 3D space. Okay. In page 40.
14, okay.
40.
Yes.
40, not 40. Okay. Figure 36.
Okay.
Okay. In this paragraph, we say that the independent paragraph determine the orientation of the solid around the point P. Where is the point P?
It's the best center of the 3D object. Just we forget to point it.
But where is the point P in our field?
Yeah, that's another part. Conservation.
Point P is other angles, and they was really expecting you to talk about other angles.
Yeah, but we choose the Cartesian coordinates, so we don't have to, we didn't want to make it more complex.
No, with Euler, it's very, very simple. Other angles is very simple.
Then we had to take another supplementary courses for robotics.
Now, did you work on this point P?
What?
This point P, did you work on it? Did you use it? This point P?
No,
If you have used it, so you need other angles. It is written in your manuscript.
yeah, but this manuscript is taken from a book, a robotic book. So,
In the same page, the presentation of the position. In the same page, the presentation of the position. Of what?
position
Of what?
of certain point of the space.
Others.
Okay.
Where? After position.
Okay.
Okay? For page 45.
45.
45. 45.
Yes.
Okay? The figure 40. It's very easy figure. I have there, I saw in this here. And
It's a representative figure of the coordinates of the missile based on the base frame of the robot. So if you can see where we have pointed the first angle, the theta 1 and theta 2, there is where the robot should stand.
where is power?
It's like that.
Okay.
Theta 2 make this orientation.
Okay. Okay. Continue.
Yeah, as you said, you have to know that the robot base frame coordinate system is coincident with the coordinate system of the target. They have the same point O, the origin O.
You can imagine it as the missile flying from point.
Imagine.
Huh?
Can you imagine?
I'm trying to explain that.
What did you say?
I said you can imagine that the missile is moving from point A, which is the missile launcher,
Okay.
and which is the center of the Cartesian coordinate system, and flying to the target
Okay.
in a projectile motion.
Okay. In the next page 46, acceleration.
Yes, we
Okay. In the paragraph, in the projectile, okay? In the projectile, 2, in the vertical direction. Okay?
Yeah.
Okay? Could you explain this paragraph using figure 5?
Figure what?
In the projectile motion, there is only acceleration in the vertical direction.
yes.
Yeah.
Okay?
If we ignore air resistance and all the other.
I want to explain this paragraph according to the figure 5.
The missile actually is affected by the gravity, which is the acceleration, G, which is equals to 9.81. On every point of its trajectory, it is affected by the acceleration, which is always vertical, on the xy plane.
It's not the vertical.
No, it is acceleration.
Vertical.
Acceleration, not the motion. Acceleration in physics, when you represent the gravity, is always vertical on the xy frame.
The missile is affected. The missile is
Can you
affected.
repeat, please?
Yeah, I said that.
I hear you very well.
For example, here we have a car walking at the street. If we want to represent the gravity,
Okay.
we should look first at the center mass of this vehicle. Then we have to design a vector vertical to the xy plane at every point of its trajectory.
And in a missile, it is the forces applied on the main forces, it's the force that making its velocity, and the acceleration is at every point bringing it down to the ground, which is the acceleration due to gravity. And the acceleration due to gravity is only vertical. There is no acceleration due to gravity in the horizontal plane.
For the page 47, question 43, time of flight.
43.
Yes.
Yeah.
Yes. The time.
Represent time of flight, TF, equal to 4.
Yes. 2.
V0.
Plus
and
3, theta 2.
Yeah.
Theta 2.
Theta 2.
Yes.
Okay?
Yes.
You know that sin of theta 2 is between
Minus
-1 and 1.
Yes.
Okay? TF can be negative.
No, but time is considered as absolute only. We have the absolute value of time.
But here, you should give range of value of
Absolute value, yeah.
you,
Okay, that's what we want.
okay?
Yeah.
I have a lot of questions, but I think it's
Bon, je tiens à vous remercier, M. Dani. Donc, avant de passer la parole au cadre, quoique l'énergie reçue le point de vue comme à la dernière minute, mais cela ne m'empêche pas donc, de poser quelques questions. Donc, comme vous savez, donc un travail normalement, on a deux côtés, il y a le côté faux, côté là. On a donc tout commencé. Donc, je dois donc vous saluer donc, pour l'initiative, la première initiative, c'est-à-dire de travail en anglais, donc sur l'innovation, donc pour la future donc promotion, donc de songer donc à rédiger en anglais, à exposer en anglais, avec une initiative. Donc, concernant votre travail, nous avons parlé de réalisation. Les réalisations, c'est des simulations. Donc, il faut carrément changer parce qu'il y a une grande différence entre simulation et réalisation. C'est vrai. Donc, c'est pas facile de réaliser ça, mais c'est une simulation.
Au début, c'était ce qui pensait
C'est vrai. Aussi, vous avez songé à faire une réalisation. D'accord? Mais ce que vous avez fait, ce que vous avez présenté, c'est une simulation. Donc, il faut carrément changer le thème, le sujet d'un thème.
C'est les directives du département.
Hein?
C'est les directives du département de changer tout.
Non, mais c'est bon, je ne suis pas content. Je ne suis pas content, mais ça empêche que ce que vous avez fait, c'est une simulation. Donc, il faut changer, changer le titre. Avec première chose. Donc, je reviens donc à votre manuscrit. Maintenant, vous avez donc un manuscrit. Première page, c'est une introduction générale, donc il faut différencier. Ce n'est pas introduction. Il m'a la question résumée dans mon profession de ça, c'est une introduction générale. Et si c'est dans les mains, si c'est une introduction générale, elle est incomplète. Parce que ça, donc une introduction générale, on doit présenter votre travail.
Mais nous, quand on faisait notre recherche dans la littérature anglaise, on trouvait le titre de l'introduction générale, c'est mon introduction. Il y a pas de titre.
C'est une introduction générale, c'est une introduction. C'est présenter ce que vous avez fait dans le nom de votre manuscrit, ce qui n'a pas été fait. Donc, c'est incomplète. Donc, vous avez l'introduction. Le contenu, c'est vrai que l'introduction générale, vous le contenu, donc il est incomplet. Parce que normalement, vous devrez présenter donc
la problématique.
Ah,
Ça, c'est la prise en charge.
donc elle est incomplète. À refaire. Là, pour l'instant, l'origine, on va faire parce qu'il y a des bons de l'origine. Donc, il y en a d'origine, il manque. À la fin, il y aura abstrait. Donc, ce qui manque. D'accord?
Résumé en
On
arabe.
le rajoute.
On peut l'ordre,
En arabe et en français. Pas de souci.
Donc je vais essayer de vous en profondre des choses. Là, vous parlez d'une automatisation. Donc l'automatisation, en quoi consiste l'automatisation?
L'automatisation dans notre projet concerne l'orientation automatique des angles, sachant que les coordonnées de la donne une position où on veut viser notre bras manipulateur, l'automatisation ici se présente dans l'orientation automatique des stepper moteurs bas à bas.
Donc ça veut dire, quand on parle d'automatisation, automatiquement, donc vous avez parlé de l'assainissement de quelques données, donc il y a le retour. Mais ça veut dire qu'il n'y a pas de chaîne à un jour, pas de chaîne, donc chaîne d'assainissement, donc automatique aussi de la. Et quand on parle d'automatisation des véhicules, généralement, ça pose problème donc, de stabilité au système et problème de précision, ce qui n'a pas été fait. On n'avait pas parlé de ça.
Si on faisait la réalisation, on faisait.
On présente, il n'y a pas de boucle. Les boucles,
On limite le travail.
je me suis manqué pour notre travail. Parce que ça automatisé, donc on va se
تصل في التوجه ما طلعش بالكريه زياده من ديال كون ديميتي
Et quand on fait de l'automatisation, donc automatiquement donc on doit songer à des boucles de régulation, donc à réguler certains paramètres. Et quand on régule les paramètres, quel est le problème de précision qui va se poser? Problème de stabilité, donc automatiquement on doit penser donc, à un régulateur. Donc maintenant on n'avait pas son. Donc signaler à la data. Pour moi, je ne suis pas contre parce que le temps, les conditions, mais je pousse les avantages qu'on doit le signaler. Donc, elle l'attend, arriver donc, vers un travail plus ou moins, je ne l'ai pas fait. Donc, ce rapprocher, je n'ai pas fait.
Mais selon ce que je sais concernant les moteurs pas à pas, ils n'ont pas besoin d'un retour pour être complètement.
vous le faites le moteur
كيف نعرف بلي لا فالور تاعك هذيك نسمي لا صوت تاعك هذيك كنا تعاوش كنا تريدوليات كنا تيجبدو لا سي البوزيسيون ريغولي البوزيسيون كلشي دوا تكريسي هنا نشوفوا الليره تاع المدام دايره بيرمانون elle est importante donc هنا صافي كل السيستم تاع هذا doit être corrigé qui nous ça fait changement quand je change s'il n'est pas régulé, donc s'il n'est pas corrigé, elle est la caractéristique. Quand je change la système, je dois recommander la même caractéristique de ça n'a pas de sens. Même la troisième, ça n'a pas de sens. Parce que le système n'a pas été corrigé pour le bien la veille et la formelle. Donc, le système qui marche. هذه لا كاركتيرستيك دو سي في الشونجمون تاع لا دوزيام داكور نو سي با لا توازيام علاش باسكو السيستم تاعنا با ايتي كوريجي كافين باش نفهم ولا دونك سي فولي كيلكو ريمارك كاين حاجه اخرى كي ممكن votre manuscrit حنا كونطون كي ندو une image bien figurée علاش دونك سي ان سيبور سي ان moyen pour expliquer ندوها كريفيرونس Ça normalement le candidat, donc je dois la signaler le texte. Ça n'a pas été fait. Quelques schémas, ça a quelques figures signalées, ça a quelques figures, mais on signale le texte. Sinon, il n'y a rien. Il faut apprendre. Donc il faut revenir vers le schéma, tous les schémas. Où les figures doivent être signalées le texte. Selon le schéma donné. Voilà le schéma. Voilà le schéma donné.
Il faut les interroger dans le texte.
Il faut les interroger.
Vous n'aurez pas présenté un cahier de charge. Vous n'aurez pas présenté un cahier de charge de votre réalisation. Au moins. Avant d'entamer la simulation, vous devez présenter un cahier de charge. Vous n'aurez pas fait ça.